So welcome. So here we are doing alternating current circuits, and we're going to do basically a few things. The first thing we're going to look at is the problem we have in visualizing it. If you were to get a oscilloscope and connect it to the mains, what you would see is basically this graph here. You'd see a time varying voltage coming out of the mains, and you could talk in terms of the peak voltage, but it's only at the peak voltage for an instant. So is that really representative of the voltage? We could talk in terms of the average voltage, but the average voltage is zero because it's symmetrical. So every time it's positive, it goes equally negative. So it turns out it could be plus or minus 1,000 volts or plus or minus half a volt, and the average wouldn't know the difference. So the average is a real problem when it comes down to characterizing the size of the voltage. It turns out that, as we'll learn in a minute, the best way to characterize an alternating signal is to use what's called the RMS voltage, the root mean square voltage, and we'll talk about that in the next section. And basically, if you have the root mean square voltage, it's kind of like there. It's about 70% of the peak value, and it basically, you can use your power law and all that kind of stuff. You can use your equations as if it was the DC voltage, and it will give you decent answers out of it. That's one thing we're going to get to. First thing we're going to look at is how we deal with this problem, which is that this cycle keeps repeating, and we'd like to be able to talk about it in better detail. What we find is that it's actually quite advantageous to represent this oscillating sine wave as a phasor diagram. The phasor diagram works on the principle. If you remember back to oscillations and waves, we had this thing where we said, if I have a pendulum swinging backwards and forwards, and I have a dot on a circle moving in uniform circular motion, the two of them will kind of stay on track with each other all the time, which meant that the mathematics I use for my circular motion is quite applicable to the oscillation, as long as it's simple harmonic. And it turns out this is simple harmonic oscillation. So again, rather than talking about being 90 degrees, rather than talking about being a quarter of the way through the wave, I could say I'm 90 degrees around my circle, or rather than being halfway through my wave, I can be 180 degrees through my circle, or rather than 3/4 of the way through my cycle, I could be 270 and so on. Or we prefer to talk in terms of radians, so this would be pi, this would be pi over 2 radians, and this would be 3 pi over 2 radians, and so on. And this is really useful for comparing when things are not quite in phase with each other. And what we're going to find is in AC, things are not quite in phase with each other. So, okay, I could pick a point on my graph of voltage versus time, and that would map to a point here, actually. It's like I did first choice is wrong. This is wrong because it comes after the peak. If you look at, there's the peak, 90 degrees out of behind, 90 degrees behind. There's the peak, and I drew it as if it was after the peak, when in fact it actually is before the peak. Yeah. It's the same value. Just I drew it in the wrong bit. So my phase angle's wrong on that. So just ignore that bit. And then this bit down here, B, is almost when I'm at pi radians out. So there's my point B. And here's my point C, which is down here. And here's my point D, which is there. So they're both useful. This first one is useful for kind of getting a feel for what goes on in time. But when you start looking at combinations of inductors and resistors and capacitors, the phase angle gets messed up. And so they look like a sine wave, but they're not quite where they should be. And it's hard to compare just two sine waves. So this is where this comes in really useful. So we say when a wire loop rotates in a magnetic field at the power station, we get a voltage which is my instantaneous voltage is equal to my maximum voltage modified by this sine function, sine omega t, where omega is the angular frequency, how many radians per second does the loop spin by, and time happens to be where I begin my clock, basically. Okay, and we saw that actually with oscillations and waves, so that's kind of interesting. And then we say, well, omega, of course, is 2 pi f, so we could say omega equals 2 pi over the period. So that's what we're playing at. Okay, we're going to use like graphs, and we're going to use phasor diagrams, and we need some way of just simply representing how much we have. Average is no good because it's 0. The peak is no good because it's only there for an instant. We developed this thing called the root mean square, and basically it comes from the problem with this is that it has negative bits, so we can get rid of the negative bits by squaring it. That was nice, we got rid of all the negative bits. Then we average what we got. And then problem is it's squared, so we root what we got. So what did we do? We squared, we averaged, and we rooted. I don't know how to spell rooted. Rooted. And for some reason, they decided to name it as the root mean square. Mean because of average, but they did it in the reverse order. I'm not sure, I don't know why. Okay, so consider a plot of current or voltage, doesn't matter, versus time. The average value of current over one cycle is 0 amps. Amps, Bonaquisti, you've got to put units down. The 0 average current implies no current, but this is totally incorrect. There's clearly current flowing through it. It's better to use the root mean square measure of current. We can use RMS voltage as well. So the best value for power would be V times I. And if you took the maximum V times the maximum I, it would be too big because it's only there for an instant. And if you took the 0 V times the 0 I, it would be no good because it's not 0. So what we do is we take the RMS V times the RMS I, and we get the power. So whereas with DC, power in DC equals my volts times my amps. Power in AC is equal to my VRMS times my current RMS. So this is kind of really good. How much is it? Well, mathematically, I suppose it's Imax over root 2 or Vmax over root 2. I just remember it's 70%. That's, if you like, 71%. Let's get picky about 1%. But it's 0.7, 0.71 times the maximum value. Cool. So I'd like you to be able to make those transitions. So an AC current has an amplitude of 10 amps. What is the RMS current? So I'd say, okay, AC current amplitude, of course, is from the middle to the end, so that's going to be 10 amps. RMS is equal to 0.7 times Imax, which equals 0.7 times 10, which equals 7 amps. News matters. An AC EMF has an amplitude of 15 volts. What is the RMS EMF? I'm going to put some numbers down. I want to get you involved. So I'm going to say it's going to be. I want to say it's going to be 7 volts. That's A. I'm going to say it's B is 14 volts. I'm going to say C is going to be. Let's have a look. 10.5 volts, and then D is going to be 12.75 volts. So which do you think it is? So you're going you're going to say V. So let's have a look. Here we are back again, and let's see what people voted. So mainly C, a little bit of A, and yeah, so it's going to be VRMS is equal to, as always, it's going to be the 0.7, which is the, over root 2 times whatever it is, V max. So this would be 0.7 times 15. And if I did my math right, that would be 7 plus a half of 7, which is 10.5. So that's the better number to use if you're trying to figure out the power dissipated in the circuit. If I wanted to know the RMS current through a resistor, it was AC. If I use the RMS potential difference, I get the RMS current. So it kind of works out well. So what you get into the habit of is, for AC, you tend to use RMS rather than peak. You don't talk much about peak. It doesn't matter that much. Okay. So let's start our process. I'm going to step through the process so you see where we're going. Okay. So the first thing I'm going to do is I'm going to look at the current versus voltage relationship for a simple. This here is the simple for the AC power supply. It's not like the DC power supply is like that. The AC power supply is like a little AC wave inside. So we have a resistor in series with an AC power supply, and I look at the graph of the current versus voltage, and I look at the phasor diagram for the current versus voltage. And then I'm going to do the same thing for a inductor. And you can already see there's more math in there. It's not really the math I'm worried so much about. It's the fact that they end up out of phase. The current and the voltage are not maximum at the same time, because the EMF in the inductor, it depends upon the rate of change of current, not the current. So it's going to be out of phase. And so we have a phasor diagram that looks kind of interestingly different, but somehow easier to interpret. I can't glance at this guy and say it's 90 degrees out of phase, but I can glance at this guy and say it's 90 degrees out of phase. And so phasors are useful. Then I do the same thing for the capacitor, and I find out, another 90 degrees phase shift. But if you look at these two, in one case the current's behind, in one case the current's in front. It's like one of those, find the star thing, find the thing that's moving. And so we see that, okay, this is also interesting. So in one case the thing leads, and in one case it follows. How significant is that? Turns out it's quite significant. I put these guys together in a LCR circuit. Why do I call it an LRC circuit? Why do I call it an LRC circuit when the rest of the world calls it, RLC, LCR, whatever? And they call it LCR, they call it RLC because it's traditional, I guess. And I call it LCR because in the phasor diagram, the potential difference, or if you like, the potential difference across the inductor leads and the potential difference across the capacitor follows. So when I do my important calculation, I've got to take that into account vectorially. So by learning LRC, I learned the order of them. You look at these three guys and you can't see any change, so they're different. I don't know, they're weird, I know that I have to, my total voltage is equal to the voltage drop across one plus the voltage drop across the other plus the voltage drop across the third. But here's the weird thing. Remember, in series, the current's the same, but the voltages add. Yeah? From DC circuits, the current through all those devices are the same, but the potential difference you have to add because they all get a bit of it. Same for this, except that these we have to add vectorially. So if one's pointing in the opposite direction to the other, they fight each other. So the L fights the C. It's kind of weird. So I end up with these kind of complicated phasor diagrams, and what comes out of it is that if I plot a graph of my frequency-dependent resistance, I'm not going to use that term, I'm going to make a special term for it. For my inductor, it looks like that. If I look at my frequency-dependent resistance for my capacitor, it looks like that. If I combine them, it looks like that. So cheating a bit. It's not. I'm supposed to add these two guys up, which means it's double the height, but I ran out of space. But clearly there's a minimum here. Minimum resistance means maximum current flow. Maximum current flow means more signal. So this is a tuning circuit. There's a high-pass filter and a low-pass filter in series. So at high frequencies you get killed, at low frequencies you get killed. In the middle you get least killed, or best. And that's the way a radio works. The antenna from the radio picks up all the radio stations in your vicinity at the same time. Picks up the strongest station most and the weakest station least. But because you tune your tuning circuit to a given L, R, and C, you have a sweet frequency where you get maximum current flow through your circuitry. And the radio station which is at that frequency is the one you hear. So this is kind of really, really important technology, and that's where we're going. That's what we're trying to get to. So that's where we're going. Let's go back and do it. So let's look at this. So, okay, so here's my circuit. It's a AC supply with a resistor, and I know using Kirchhoff's rule, my potential difference in my EMF, which is delta V, added to my potential difference across my resistor, which is delta R, must sum to 0. Well, you know, I'm saying, I should maybe say plus negative there, but these two added together must equal 0. Okay. And I know, because I know the shape of this, that delta VR, that's my power supply, is equal to delta V max sine omega t. So if I try and find my current flow through my resistor now, it's going to be I equals V over R. So there's my V bit, which is time dependent. And there's my R. So I have some kind of constant times a sine omega t. And, you know, my delta V max over R is going to be my I max times omega t. And the important thing I'm going to look at is this trig function. That's sine omega t, and that's sine omega t. So for any given t, because they've got the same omega, we have the same phase. And what that means is the maximum in your voltage causes a maximum in your current, or, you know, maximum in your current causes the maximum potential difference. You can run it both ways. And your minimum in your voltage corresponds to the minimum of your current, and 0 in your voltage corresponds to 0 in your current. It's beautiful. And you plot these guys out, one in red and one in blue, and one big and one small, so we can see them. There's no significance to that. I just picked one big, picked one small. But they are in phase. So after a split second, they would both be there, and after a bit later, they'd be there, and they'd both be there, and they'd both be there, and they'd both be there. And then at that point, there'd be their maximum, which is that point there. And then they'd be here, which is that point there. And then they'd be here, which is that point there. And then they'd be down here somewhere, which would be that point there. And then they'd be down here at the minimum, which would be that point there, and so on. Yeah. The key thing I want you to think about is two things. What's the phase relationship between them? And then the second thing is, I want you to look at this. The current is equal to my Vmax. The maximum current is equal to my Vmax over R. I just want you to look at that pattern. We're going to do a lot of comparing patterns in this section. Okay, a lot more math, but what's it saying? It's saying, okay, let's have an inductor with an oscillator. And we know from Kirchhoff's rules that the combination of my two voltages must equal 0, because there's no, you know, remember the EMF is balanced by the potential differences. And I know an expression for my voltage drop across, by my potential difference across an inductor. It's minus L di by dt. Now, here's a little thing. In AC, they often represent current as little I rather than big I. And if you're not sure about that, you tend to think, where's this, you know, Where's this imaginary number come from? And it's not. It's just another way of writing down AC current. Okay. So it's L di by dt. Okay, so now let's do a bit of math here. So there's my original voltage in time. And if I substitute in, then from this equation here, I can see that that is equal to that. And that must equal that. So then my di is equal to that, just rearranging. And then let's do a bit of integration. Well, we're always going to cheat. So my integral of my di is my current. And then I have Vmax over L, integral of sine omega t d by dt, which gives me cosine omega t over omega L. Yeah, that makes just doing some math on it. There's a negative sign in there. Okay, so that's the right answer, but it's not in the form I want. So then remembering, I don't know if you remember it, but you know, cos omega t equals minus sine omega t minus pi over 2. If not, just get comfortable with it. Substitute that in, so I get, oh, so this is equal to Vmax over omega L sine omega t minus pi by 2. I'm going to compare that guy there with that guy there. And I wanted it to be in sine. Why is this no good? Because it's a cosine. But you could look at it, and say the cosine and the sine are always 90 degrees away from each other. Agreed? Yeah. So I could have got my answer, you know, kind of like hand-wavingly just at that point. Said, oh, look, it's a cosine. Oh, look, it's a sine. They must be 90 degrees away from each other. But this is a bit more, you know, rigorous, where I go, oh, it's not just 90 degrees. This current is 90 degrees behind. Okay. So that's what it looks like on an oscilloscope. And as I say, I can't glance at that and say it's 90 degrees behind. I suppose I can, but I can't say it's 90 degrees. It's not obvious to me it's 90 degrees, although that one is right over that and that one is right over that. So you could figure it out. But this is obvious, yeah? I can see a right angle, and that's a right angle. The thing I wish, this is the way the book does it, and the thing I wish is that, and I guess, I kind of wish they'd drawn these so that current was always in the same position rather than voltage. Because the current's going to be the same through all these three different components in the end. So we're going to compare voltages, not currents. But okay, whatever. And then if I look kind of here, and forget about that, because who cares about that? My maximum current is equal to, well, in terms of magnitude, is equal to delta Vmax over omega L. Before we had delta I max is equal to delta Vmax over R. Do you remember that from the previous page? Ohm's law. This is a bit like Ohm's law. And so I define XL is equal to omega L. So I'm not going to call it resistance. It's behaving like resistance, and it's got the units of ohms. But for some reason, they don't want to call it resistance. So they call it reactance. And they don't want to give it the symbol R, they give it the symbol X. XL is the inductive reactance, and XC is going to be my capacitive reactance. But it behaves like a resistance. It's a frequency-dependent resistance. And I think it's important. So you've got to know that equation. And I think it's also important to recognize that if I have my frequency increasing, this is the frequency of my oscillator that's driving this whole thing. If my frequency is increasing, then my resistance of my inductive reactance just increases with omega. Because L's constant, a certain inductor has a certain L, omega is the only thing I can change. It's a nice linear relationship. So, in terms of resistivity, an inductor lets you pass at a low frequency. Because it's just a piece of wire. It's just like, you know, wire don't have much resistance. But at high frequency, as you try and change the current rapidly, it kills you. very high resistance for high frequencies, low resistance or zero resistance, low resistance for low frequencies. And it's nice and linear. Okay, so a couple of things out of this. One was we got this phase relationship, and the other thing was we got this inductive reactance. Let's play the same game. We've got capacitor. Okay, capacitor. Yeah, my loop rule says they must sum to 0, and that means that my EMF and my potential difference across my capacitor must be equal in magnitude. And I can say, well, you know, I know the potential difference across my capacitor equals the charge on the capacitor times the capacitance of the capacitor, and I know that my EMF is equal to delta V max sine omega t, because that's the system that I'm choosing to use. So delta V max sine omega t must equal Q over C. So rearrange. I get this C times delta V max sine omega t equals Q. If I differentiate, dq by dt is equal to omega C delta V max cosine omega t. And just remember that dq by dt is equal to I. Okay. And if I recall that cos omega t is equal to sine omega t plus pi by 2, substitute that in, because this is right, but again, I'd like it to be in terms of sine. So IC is equal to omega C delta V max sine omega t plus pi by 2. So I compare that guy there, that guy there. Is that my machine? Is that inside the room or outside the room? Uh-oh. It was nice knowing you. So we see that it's 90 degrees. It's going to be 90 degrees in front. The angle is whatever it is plus 90 degrees. So again, I look on here and I see that, and I see there's a nice right angle here. And again, I wish they'd kept the I at the right same angle and changed the V, but they didn't. And again, looking down here, I see, oh, this is like, well, I've got to be a little bit tricky here. Now I'm saying, oh, I want something. So I said I max is equal to delta V max over R. And then I said, well, oh, by the way, I max for an inductor was equal to delta V max over XL. And I said, well, by the way, XL is equal to omega L. So now I said, this is a great idea. I max for my capacitor will equal delta V max over XC. So now I say, well, what is XC? And I have to look over here. And I say, well, if that is going to become, that's 1 over omega C. Yeah, because we want the XC underneath. It's going to be 1 over omega C for XC. Yeah, that equals 1 over omega C. So when I put it in, it goes on top. The omega C goes on top. And I think the other important thing to recognize is if that's resistance and that's omega ohms, the resistance of the capacitor versus frequency, it kind of like it's an inverse, and it's an inverse dependent upon omega. Okay, know that equation. So what is the reactance of a 5 Henry inductor when 5 radians per second AC voltage is applied to it? So what is my reactance? XL is equal to, what's that equation again? XL is equal to, what was it? Omega L? Yeah. So that's going to be, omega is going to be 5 times my L is going to be 5, which equals 25. And what's that going to be in, what are the units of these things? It's resistance, isn't it? So it's going to be ohms. And then what is the reactance of a 10 farad capacitor when 54 hertz. Oh, I'm being a bit devious now. So XC is equal to 1 over omega c. But omega is not given to me. I'm given f, frequency in hertz. So I got to remember that, oh yeah, omega is equal to 2 pi f, which equals 2 pi, well, let's do it in a bit. So that means that xc is equal to 1 over 2 pi f times c, which equals 1 over 2 times pi times 54 times 10, which is a number. And I've forgotten, this is day 3 of me forgetting my calculator. It's like, I'm clearly, it's near the end of the semester. So that worked out to be a number, yeah? Anybody got the number for me? 2 3s are 6, 6 10s are 60, 60 times 54 is 0, 6 4s, 24, carry 2, 6 5s are 30. It's going to be slightly bigger than 3,240 ohms. Yeah, so slightly bigger, about. I just used pi as 3, I don't, ohms, yeah? I mean, why? Oh, it's over that, 1 over that. I meant 1 over that. 2.95 times 10 to the minus 4. Good, thank you. What is the resistance of a 10 ohm resistor when a 25 hertz AC voltage is applied across it? And this is just me being, R is equal to R, which equals 10 ohms, just to see if you're following through on it, yeah? Yeah, cheeky. They're the worst things because you kind of put them in and it's half a joke and it's half a gift and somebody will just be stuck on it and they will fail the rest of the exam because of this. And you point it out to them and you can see the kind of like the disappointment, the disappointment and the rage. And you go, it's just a joke, My daughter's 12 and anyway, so okay, let's do the next bit, and the next bit is put these guys together. So LRC, consider a series network consisting of resistor, I got to get the order right, inductor, resistor, capacitor. Why not just get the order right again? The current at all points in the series AC circuit has the same amplitude and phase. The current is constant through a series bit, yeah? Okay, so it's going to be the potential differences that are going to switch off. The instantaneous voltages are out of phase with each other. So if I look at this graph and I don't like these graphs, I don't use them. I like them, but they're not that useful in this bit. But here's the voltage across the resistor, and here's the voltage across the inductor, and here's the voltage across the capacitor. And I can represent that mathematically. And the important thing, it doesn't matter about that. What matters is that when we add these guys up, we've got to add them up, if you like, vectorially. So we go to this next, sorry.
Is the delta big V voltage and the delta little v instantaneous? Is that the difference?
The delta big V is the maximum voltage.
Yeah.
That's poor nomenclature on my part, but that's the maximum voltage. This is the maximum voltage, and this is the time varying voltage. Yeah. So I'm talking here about the time varying voltages and just, okay. And what I mean, well, this here, I think of as your potential difference there, which is the same as your EMF there, if you like, yeah? Okay. So let's draw that out as a phasor. Current's going to be the same, so we're going to have our inductive, the potential difference across my inductor is going to lead by 90 degrees, my potential difference across the capacitor is going to lag by 90 degrees, and my potential difference across my resistor is going to be in phase with my current flow. These two guys are clearly fighting each other. 6 volts upwards, 3 volts downwards, fight. So really my overall effect is the vector sum of those two with the vector sum of that guy giving me a kind of answer. And I don't really care so much about that, because what I want to get to is the resistance in ohms of my network. That's really what I want to get to. So I say, well, hold on. This is like saying that I have the resistance for my resistor at that phase, and I have my net resistance or reactance of my capacitor and my inductor combined together there, and there's my total resistance, which is called my impedance. That's what I really want, because as my impedance falls, my current increases. So that's the game I play. So what I do, and this is from the book again, but what I do is I draw my phasor diagram in terms of XL, in terms of XC, and in terms of R. And then I find my Z. That's the skill that I think is really important. And I find my skill using Pythagoras' theorem for this. 2 dimensions, but Pythagoras' theorem. This is R squared. This is the difference between my XL and my XC squared. And I know my maximum voltage equals my maximum current times my impedance. And this is the thing I want. This is the thing I want to. As the frequency changes, it is my impedance that's going to change, and so I'll mess with these things and get a bigger Imax or a smaller Imax depending on Z. And there's phase angle. The phase angle is that guy there, which for me is that guy there. So the skill, I want you to be able to calculate your XL, your inductive reactance. I want you to be able to calculate your XC, which is your capacitive reactance. I want you to be able to draw the phasor diagram with R so you can calculate your impedance. That's the skill I want. Okay. And phase angle. And why am I doing that? Because my impedance is basically the sum of these guys, and it's going to basically have a pattern that kind of looks like this. And what's going to happen is when that reactance is balanced by that reactance, my impedance equals my resistance. So my minimum resistance is my R. So I want to do one.
And XL will always be 90 degrees ahead of your
Yes. Because that comes out of the math originally, yeah. Autosave. An autosave file exists. Load it now. Cancelled. Okay. Wait a moment. Okay. So I got my pen. I've got my pen. Yeah, it's on the side and everything. That's not bad. Okay. So let's do one. Man, that noise is really annoying. Let's have this as, I don't know, 10 volts AC. Let's have this as 5 Henry, 6 Henry. I know the balance a bit better, so I'm gonna try and make it. I might have to cheat at some point because I want to get these guys reasonably in balance. So I'm going to turn around and say that this is 4 times 10 to the minus 3 farads. I'm going to say that this is 10, no, can't have 10, can I? 18 ohms. Now, I'm making those numbers up, and maybe I pick wisely, and maybe I pick not so wisely. I'm going to figure that out. skill number 1. XL is equal to omega L, which equals, oh, got to tell you the frequency as well. Oh, no. Okay. I'm going to jump ahead a minute. The resonance frequency for this, omega naught, that's the frequency that it is tuned at. I can tell you what's going to have the best frequency. And basically what I say is, in fact I can, boom. If I go down here, let's just show you that briefly. Because it's a little bit out of order. Well, I guess they don't care about it. This resonant frequency, this is in terms of current, so it's the opposite of our opposite of our impedance. This omega naught is simply given by 1 over the LC. That's what it's simply given by. Can I work my way back? Can I work my way back? Can I do that and ignore what I just did? Discard. That did not go so well. Let me go here. Okay, yeah. So 1 over square root of omega L of LC, sorry, yeah? 1 over square root of LC. So omega naught equals 1 over the square root of L, which is 6, times C, which is 4 times 10 to the minus 3, which equals 1 over square root of 24 times 10 to the minus 3. Can somebody got a calculator? Can somebody work that out for me, please? It's 0.024. 6.4 radians per second, yeah? Can someone check it? Just because it's, you know, if I pick a wrong number, it's going to, the calculation won't go so well. So just double check that. Not that I don't trust you, but, you know.
That's what I get.
Good, yeah, good, okay. I mean, says the guy who doesn't have a calculator. I mean, you know. So then, okay, so I'm going to go, let's do it this way. We got time, I think. No, let's do it just as I do it in a test. I would ask you for that. And then I would say, oh, because I've already worked it out. I'm going to say, oh, let's go to 5 radians per second. So let omega equals 5 radians per second. So I'm taking you away from the resonance. So at 5 radians per second, this will be 5 times 6, which equals 30 ohms. And my XC is equal to 1 over omega C, which equals 1 over 5 times 4 times 10 to the minus 3, which equals 1 over 0.02, which I think is 50. Is that right?
Yep.
50. And then I'm going to say, well, my R, of course, is equal to 18 ohms. Okay. So there's my first set of skills. My second skill, that's going to be XL. That's going to be 30. This is going to be XC, and that's going to be 50. And this is going to be R, and that's going to be 18. Now, can you see that when I add these two guys together, I'm going to end up with that as my answer. And I'm going to go like that. Let's get rid of that. I've been maybe needlessly picky, but so my Z is going to be like that. Yeah? Can you see that? Just by the diagram. 30 plays 50. 30 is added to minus 50, so it's going to be minus 20 and all that, yeah? So I say Z is equal to the square root of R squared plus XL minus XC squared. So Z is equal to the square root of 18 squared plus 30 minus 50 squared. So Z is equal to the square root of 18 squared plus, that's going to be 20 squared. And what does that work out to be? It's going to be about 20. It's going to be something in between. It's going to be like 19 or something like that. What's that going to work out to be? $26.9. Oh, I'm out. 26.9. Okay. Yeah, you're right. Okay, ohms. That's my Z. And my phase angle, which is that guy, my Z is equal to, what's the opposite, which is the tan, so the -1, or the opposite, which is 20, over the adjacent, which is 18. I'll sort out my signs in a minute. So can you just work out what the magnitude of that guy is? 10 to the -1 or 20 over 18. That's 20. This is 18. Yeah. So what is that in, pardon? Sorry?
0.84.
Is that in radians?
Yes.
And you can work in degrees if you want. You can put it in degrees. Can you just do it in degrees for me?
48.
Sorry, 28?
48.
48, yeah.
Would it be
Now.
negative?
So that raises the issue of, nomenclature. Some people, strictly speaking, I suppose it's going to be that angle there, if you want it as a positive angle. So you could say phi is equal to, let's look, 360 minus 48 is 312, or minus 48 degrees. That's, But frankly, if you had a diagram and you said 48, I would not care, because, that's the scale. Can you work out the resonant frequency, the tuned frequency? If I take you away from the tuned frequency, can you work out your Z? Can you work out your phase angle? Okay. I'll go a little bit further, but let's have a look. How do I get away from you? Do I do that? Yeah, okay. Was that a question? No, okay.
Yeah, it was. When we, in this part, when we're doing Z, it's not as important, but when we do the XC minus XL, or XL minus XC, does it matter which way that it goes? In this one, it's not much of a difference because we're squaring it. It doesn't matter if it's negative or not, but...
So I'd like it the right way on your diagram, and I'd like you to do it the right way. But you're right, if you get it the wrong way, it doesn't matter, because you're going to square it. But down here on the phase angle, your diagram would be wrong. So I want you to get the diagram right. So yeah.
L is leading.
Yeah.
Capacitor is trailing.
L is leading. That's another way to do it. L is leading. Yes. Maybe there's no need to learn it in that weird order. Maybe just say L always leads. But I think I'm starting a movement here. I'm going to
It's called the Dark Christmas circuit.
along with the method and the, I always wanted a theorem, So yeah. So that go away. Yeah. Okay. So I erased all my writing from the previous. So okay, power. Let's talk about power. So what is this saying? This is basically saying. Let's get a pen. So this is basically saying, look, no power losses are associated with pure capacitors and pure inductors in a circuit. They're not resistive. Well, no, they are. but it's the resistor that dissipates heat. They don't dissipate heat. They create electric fields, they create magnetic fields, but they're kind of conservative, I think. So power is converted into heat in the resistor. For an RLC circuit, the instantaneous power is, it's going to be my, my current multiplied by my voltage, which gives me that. If we remember, I don't know if you remember it, I don't remember this, but well, maybe I do. Yeah, actually. So sine omega t plus phi is equal to sine omega t cos phi minus cosine omega t times sine phi. And substituting in gives you this complicated thing. And so the average of sine squared omega t is 0.5. Okay. So I get that, and then I come down here, and I end up with this, and this is like the take-home I squared R, like we had for DC circuits. So just stick in RMS, and all your DC stuff becomes your AC stuff. It's like, this is, I guess, just justifying it because it's AC. So is it the same? Yes, it is the same. Okay, so we decided that a graph of resistance versus omega would look something like that. And if I recognize that so if a graph of Z versus Z in ohms would look something like that. And so big Z means small current, little z means big current. So on this graph here I have small currents when I'm off resonance and big currents when I'm on resonance. That makes sense. It's a very nice and symmetrical graph, and you're going to do a lab in this, and you're not going to get this nice symmetry. If you think about it, if that bit's linear, and if one bit's linear and the other bit is inverse, it's not going to be symmetrical. Okay, fair enough. We can live with that. And the interesting thing is that your minimum impedance is your resistance, and so the current flow gets bigger at maximum for a smaller resistor. So a 3.5 ohm resistor has a bigger peak than a 5 ohm resistor, which has a bigger peak, which is a bigger peak than a 10 ohm resistor. And if we look, we can see there's a sharpness to this. And so, frankly, if I wanted a tuning circuit, I'd sooner have this top characteristic rather than the bottom characteristic. Because if I have a radio station there and a radio station there, this is a much smaller fraction of that. But that blue line and that line, I'm going to hear kind of both of them, And I really want to only hear one of them. So I'd really like very sharp, narrow peak, and that's represented by a thing called the quality factor. We say a series RLC network, going to finish soon, series RLC network is said to be in resonance when the current has its maximum value. There's the maximum value. Let's multiply it out. The impedance is current depend upon frequency. The resonant frequency is that. Know that actually. So know that. Be able to find this omega naught. And then for the next one, we have this thing called the quality factor, which is the basically the resonance frequency divided by the width at half max. If you want a big number, you want a big frequency with a narrow little width. So omega naught over delta omega, not the other way around. And you see that your quality factor depends upon L and it depends upon R. If you buy an expensive system, it's not got just 3 components inside. It's got lots of components inside because there's lots of filtering and sophisticated circuitry. So we're doing the fundamental circuit. We're doing the thing you can buy from Mozy in a little thing called a crystal radio, and you make it and you put a little earbud in and you can kind of hear the AM stations, and you can hear 5 of them at once kind of thing. It's not particularly good, but it's okay. Then the last little thing, and this is going back to our mutual inductance. The reason why DC lost out to AC is because of the inability in DC of easily changing the voltage and current without a lot of losses. I can make voltages smaller by putting resistors in my circuit, but you know, I've got a lot of heat generation. With the AC system, I can use magnetism. So just like we have the cordless toothbrush with a coil on the inside of the handle and a coil on the base talking to each other, I can do it even better if I put a metal yoke around this thing. And so all the flux that I generate coming out of this guy actually goes into that guy. All the changing flux is a changing flux through that. So what I end up with is, and the way I remember it, is the ratio of my voltages, so delta V1 over delta V2, is equal to the ratio of my turns, which is N1 over N2. And if I rearrange it, delta V1 over N1 equals, so it's the same equation. But I find it easier to remember delta V, the ratio of my voltages is the ratio of my turns. And so I can switch between a low current and a high voltage, which is great for sending things long distances through the countryside. And I can, when it gets near my house, I can change it for a high current and a low voltage, which is great for not getting shocked. And that's the game that power companies play. They jack the voltage up to hundreds of thousands of volts and ship it across the countryside. Very little current means very little heating loss. And then it gets to your house and you have a substation in your neighborhood and you'll have a little trash can on a pole at the end of your street or in your house, and your wires come out of that, and that's another transformer. And then you take it into your house, and ironically you use a whole bunch of transformers. Those plugs that have big square plugs, they got transformers inside, and they're actually changing the voltage and rectifying it to DC in many cases. I'm going to know that equation, be able to play with that. So when I look at this, I want to run out of time, so I've got to be careful. I really care about the transformer. I think it's great. Quality factor and that bit are really important. And then if I go back, my root mean square is important. So 3 bits. Yeah, I'd say 3 bits on that. I'm going to just pause that there so I can finish off my recording in 1 bit.